Alright, welcome back to our series on designing a computer from scratch. This section we're calling Appendix B2, and it's a continuation of the board-specific interfaces. In the last video we drove the SDRAM and Ethernet interfaces to inactive levels so that those chips are not being turned on accidentally. This video will begin driving the functions that we want to use with the CPU. The CPU resources we can use pretty easily would be the USB port. We've already, we know it already is hooked up, so that's good. The 7-segment display, it's a 3-digit 7-segment display. We'll make that work in this video. And the I/O connectors, there's a long I/O connector down the right side over here, and there's these 3 PMOD connectors across the top. This video we won't get to those, but we'll get through the first 2 things and do a major change to the CPU design itself as we're going along. Those 3 devices, or 2 of the 3 devices, the UART and the 7-segment, there's projects and example code for them, so we can grab the pinouts that way from the QSF files. We showed how to do that in the previous video. One part that was a little bit ambiguous perhaps was when it said UART transmit or UART receive, was that out of the FPGA or into the USB to serial bridge. And looking at the schematic confirmed that USB UART is transmitted out of the USB to serial and received into the FPGA. So it truly is UART receive in the FPGA. To add the UART loopback, we'll just do a loopback for now. We'll take the data that you type and send it back in. Basically, it's pretty simple. Just add the 2 entity pins for UART receive and transmit. Those match the pin file names that were in the QSF file. They're not NAND compatible, but I really just thought I'd leave them the way they are for the moment. It's just easier. Create a single wire here for looping back that serial, and then take the receive and put it on that wire, and then take the wire and put it on that transmit. To test it, we're running Putty. You can run any serial type of program that does USB serial, but Putty is the one that we tend to use. Baud rate really doesn't matter, but we did set it to 115/200 because we wanted it to be sort of at the upper end. One thing to notice about this part while we're thinking about it is these 2 pins, RTS and CTS, the hardware handshakes, are not hooked up to the FPGA, and this is my pet peeve with all of these types of designs. I don't need the one handshake that tells me to slow down ever. That just is never a problem. But the handshake where I tell the host to slow down, that really does matter. And not having that hardware handshake on all of these FPGA cards is, in my book, a serious deficiency. Hey, at least hook up the one, I forget which one it is, that's the don't clear to sender requests and just always confuse me. It's one of the 2, the one that I would send out to tell the host to stop. That to me is just a serious deficiency of these parts. Anyway, enough of that rant. I set it to 115/200 baud, no parity, 8 data bits and 1 stop bit. This is what the Putty configuration window looks like, and make sure that you have the no flow control set, because the flow control will not be active. They don't even pull it on the part, so it's not like it's even usable. If you turned it on, I wonder what would happen. Well, that pin's floating. I imagine it would pull to a go-ahead state, but I don't even know that for a fact. If you look in Device Manager on my PC, it shows up as COM13, and it's the Silicon Labs CP210X USB to UART bridge. So when you hook it up, make it run, tell it to run Putty, and then you type on the keyboard in the Putty serial window, it comes back. So I typed testing, and testing came back. Well, it's not a UART yet, but it does verify that the USB to serial interface works. It doesn't prove the baud rate's set correctly coming in, but that's very likely to be good. But at this point, we could toss in the multi-comp buffered UART. We're going to skip it for now, but maybe we'll throw it in another video or 2 after this. It'd be pretty easy to add that buffered UART and actually have some serial in and out of the CPU. Nice. That would be a fun place to start. 7-segment pins are also in those QMTech files in the Project 6 7-segment LED QSF file. So I grabbed that list, and we're going to use that same pin list. The previous video described the process of grabbing those pins. I won't go into it here, but you just want to be careful to not have that file get overwritten. You can get yourself in a painful spot that will take some unwinding to do. And basically, the way I solve it is just close the project when I'm editing this file. It will reload this file when it runs, but I first create the pins inside of the entity of where they go. I close it without compiling it, and then I set these assignments and then run and compile again, and it works. You can see more details in the previous video. The process, as I said, was described in the previous video of how to do that. Code example that they have in that file, unfortunately, it's all in Verilog, and I don't speak Verilog, I just speak VHDL. But it gives you an idea. We'll use the same signal names, of course, because that's within the pin file, and we know from here how big the bus is, and we know whether it's an in and an out. And I didn't bother to. I sort of converted it to VHDL. I actually went off and found a VHDL file that already had it in. I'll put information up about that as we go along here. Those added to the CPU entity, those items, and then created a peripherals folder to put this in. I'm going to start loading all of the peripherals we have into that peripherals folder and keep the clutter down in the CPU folder. And it's not really part of the CPU, it's part of the board specific file. I could almost call it BSP, board support package, or some other thing, but I did name it peripherals. And created a new VHDL loadable file name is loadable underscore 7-segment display underscore 3led.vhd. So I've got a bunch of these on different cards. I think I just grabbed one of the 4-digit ones I had before, 7-segment 4 digits, and just tweaked a few things in it to make it work. As usual, the bit order was different and the sense was different, and had to fiddle with that a little bit, but got it working. The page that I pointed to or went to is fpga4student.com, and they have a real nice write-up here on what the segments are in a display. And the particular display that's on this QMTech card, you have to drive the SIG-scan line high to turn on a digit. You can only do them one at a time. The way it's driven is inverted by a transistor driver, so you only want to turn on one segment at a time. If you don't, it just looks weird. I mean, you're getting something on multiple segments. The other thing is to turn on a digit, turn on the segment of the display, you also drive it high. It's not inverted, so that gives you one side. If you drive it high, the inverter drives it low, and then you drive this side, it'll turn on that LED. And the order is different, perhaps, than what some of these other ones were, but the order of the pins in that these 7 segments, the SMG underscore data is the decimal point, then the letters G back to A. Once I figured that out, it was a matter of just reordering the table. That basically the file I had was this, and I'd grabbed this years ago. Left the company, the web path in it, so that if you wanted to find it, you could go back to the source for it. Now, at this point, I was faced with an extremely tough choice because the number of peripherals is going to quickly escalate. And the choice was whether to add an entity above the CPU that has the CPU and calls the CPU and peripherals. That would break the top name. That's the thing I didn't like about it. The top will no longer be called CPU 001. But the big, huge advantage of it is the CPU is left as a standalone element at that point. It's down to a very simple interface. The other possibility is to add the peripheral unit below the CPU, but then porting this to other applications and other FPGA cards would just be that much more complicated. It's much easier to change things at the top, leave the CPU in place, and drop it. If you want to clone it for another card, just clone the whole project and change that top file to change the peripherals around to support what you actually have. So I made the really tough choice to change to break the name. The top is no longer CPU underscore 001. It's now called CPU in uppercase top. So it was a bit of work to do it, but it basically took that CPU file and split it into two files. The real reason I didn't like was just this idea of passing from the CPU entity. If I put the peripheral below this peripheral set below the CPU, then everything has to pass up through that peripheral interface, and it has to go out on I/O pins of the CPU, and it just isn't worth the effort to do that. It's much easier to drive all of those I/O pins from the entity at the top, and if there's sub things that drive it, well, they're hooked up there, but I don't have to drive it through something up to there. The choice here shows the new architecture. CPU top is everything inside of it. It's got the CPU, which inside of that is the ALU, gray code, program counter, register, file, the ROM. But at the same level as the CPU, in this case, is the loadable 7-segment display and the slow clock. I kept that. So as we add peripherals like UARTs and such, they'll be at the same level as the CPU. The really good part about it was the CPU entity itself is now trivial, or relatively trivial. The only thing that comes into it that comes from the outside world is that 50 megahertz clock. Everything inside of that entity is driven off of that clock and derivative of it, and the peripheral bus then hooks up through it. So it's a lot more like a real CPU chip, where all the peripherals, a 1970s CPU chip, not like a modern one. The top is more like a modern one where you have all the functions inside of it, but in any event, the CPU is now its own standalone thing with really the clock in and then the peripheral data address and control lines. Much easier. This should be much easier to support other new designs. But if you just want to play with the CPU part and you want to make your own peripherals, you can grab the top and delete a bunch of stuff out of it, or just grab the CPU and do essentially what my top does with whatever peripherals you want to play with. At this point, we need a peripheral memory map. I guess it would be called memory. It's not really memory. I mean, there's peripheral address, so I guess it's peripheral memory map, but it's the I/O space map. And currently, we only have 3 things. We have an LED that we can write to. We have a key. Well, the key should just be read. That's a typo right there, not read write. And we put both the key and the LED at the same address, and both only use the D0. The differentiation between these two is whether it's read or write. Now, also the 7-segment displays are an address 2 and 3. I skipped 1. I just wanted these to be binarily consecutive. The bottom 2 digits of the display are driven by this address 2 with the values in D0 through D7, and the upper 1 digit is driven by, at address 3, by the values in D0 through D3. So here's a piece of test code, and it kind of shows some of the beauty of having a lot of registers, because you can preload everything you would want to do. I'm loading up registers 1 through 4 with the things that I want to write to the 7-segment displays. The code here at start reads the push button into register 0. It'll then write it out, so if you push the button, the LED will light. It'll then test the push button, and if the push button is equal to 0, it'll go down and load the 7-segment display, lower 8 bits and upper 4 bits, with what's in registers 3 and 4, which is 0, 0. The flip side is if you release the button here, it'll if it falls or then branch back to start. Sorry, if you didn't take the branch, it'll write out what's in registers 1 and that should be 1 and 2. 2 and 3 are the same, but that should be 2. So it should write register 2 to the screen. Since they're the same, it doesn't matter. But just showing some of the flexibility you can have. You can, instead of loading and unloading registers or loading registers with new values for every write, you can set them all up once and then loop down in here. Sort of shows the power of that, with that error of, hey, the wrong register, but hey, what the heck. Hate it when that happens. Press key 1 and it worked in spite of the code error there. LED 1 lit when I pressed the button, and the 7-segment display shows 0, 0 and 0, 0, 1. Remember that the key is in an inverted sense. So it demonstrates that the CPU refactoring of the into separate entities for a new top, and then just the CPU with the peripheral bus below that was good. The top is good. The peripherals work, the small set of peripherals we have. And man, that CPU entity is now just the CPU. It's not all the peripheral stuff. It's not all the slow clock. It's not all the other little pieces. Everything else is now up at the top. And the top itself is not particularly cluttered. You can look in the GitHub and see it. I've checked it in with a key branch tag. But the code is a lot less messy in both peripheral and the CPU. So it's really doing the thing that it should be doing, with the instance of the CPU inside of the top, and the top calling out some of the peripherals, and some of them are just locally done. I think it makes a lot more sense. The tip is up in GitHub under the design CPU address or location, and the branch that I made is the CPU underscore top. It's not going to be called CPU 001 anymore. That's a typo. The top level entity is now CPU top. I'll change that next time I do a video. But it's here, the current branch is CPU top underscore part B2. So hopefully that was worth doing. If you feel like checking it out, it's quite a bit different than it was before. If you're still playing around with older videos, you might want to stay on the branch you're on. I don't know of any bugs in here. This is doing some significant amount of stuff. I'm sure there's bugs in it somewhere. If I find them, I'll put them up. But in the next video, I should be able to get to working on the I/O pins and try to hook stuff up to there. I mean, we're essentially doing the same thing where we're reading the key button and writing to the LED. It's just more bits and assignment. It wasn't trivial to do because there isn't, at least in what I could see, anything in the QMTech files that show those pinouts, and that'll be just a bunch of typing, and we'll get to it. All right, thanks for watching. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindy where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.